Welcome back. Chapter 7, Section 7.5, the Central Limit Theorem. Here the focus points are: for a normal distribution, use mu and sigma to construct the theoretical sampling distribution for the statistic x bar. For large samples, use sample estimates to construct a good approximating sampling distribution for the statistic x bar. Learn the statement and underlying meaning of the central limit theorem well enough to explain it to a friend who is intelligent but doesn't know much about statistics. Okay, so the x bar distribution, so this is a sampling distribution given x is normal. So you are told x is normal, you have collected samples and taken x bar for each sample and drawn its distribution. In section 4, we began a study of the distribution of x bar values, where x bar was the sample mean length of 5 trout caught by children at the Pinedale Children's Fishing Pond. Let's consider this example again in the light of a very important theorem of mathematical statistics. Okay, so looks like the theorem has not been mentioned here. Okay, it's coming around. All right. Now, suppose a team of biologists has been studying the Pinedale Children's Fishing Pond. Let x represent length of a single trout taken at random from the pond. This group of biologists has determined that x has a normal distribution. This is an important point to note. We already know beforehand that x has a normal distribution with mean 10.2 inches, standard deviation sigma 1.4 inches. Question is, what is the probability that a single trout taken at random from the pond is between 8 and 12 inches long? Well, you have something normal. We have seen such problems before. So what do? You standardize it. X minus mu over sigma. Mu is 10.2, sigma is 1.4. So Z is this. Given any x, you can standardize it. Now x is supposed to be between 8 and 12. So standardize 8, standardize 12. When I standardize x, I get z in the middle. So z has to be between these two. Now, what's the purpose of standardizing something? You can use your tables. A bigger left, so z is between these two. So the left area corresponding to 1.29 is this. Check for yourself. 1.29, positive 1.29. Right, 1.29. So I need 9 is the last column here. So 1.29, 0.9015. 0.9015. Negative 1.57. Negative 1.57. 7 is this column. So this number, 0.0582, negative 1.57 gives me 0.0582. So that tells me, so the bigger area minus smaller area gets me the actual probability that is randomly selected sample, trout, one randomly selected trout is between 8 and 12 inches. That's this probability. That is single trout. Now, what is the probability that the mean x bar, length of 5 trout taken at random, is between 8 and 12? Now, it's the mean now. You have 5 trout, you want to take the mean x bar. So let mu x bar represent the mean of the distribution, then tells us mu x bar is mu. Okay, so what is this theorem 7.1 that they are talking about? So this is the central limit theorem, which is in section 7.5. Okay, so let's get that ready. So this is section 8, chapters 8. So here comes a section 7.5. Central limit theorem. Okay, for a normal probability distribution. So that's the example that we are looking at. Your x is normal probability distribution. So central limit theorem for normal probability distribution says, if the norm, let x be a random variable with a normal distribution with mean mu, standard deviation sigma, then x bar, let it be a sample mean corresponding to random samples of size n taken from x distribution. Then x bar distribution is also normal. The mean of x bar is mu. The standard deviation of x bar is sigma over square root n. Sigma being the standard deviation of my original x. So the mean of original x continues to be the mean of the distribution x bar, and the standard deviation of x bar is the original sigma over square root n. That's what we are going to use. So the mean of x bar is the same as original mean, which is 10.2, and the standard deviation for x bar is given by the original standard deviation over square root n. So that will be the standard deviation. So using this mu x bar and sigma x bar, you are going to standardize it. So x bar will be z now will be x bar minus 10.2 over 0.63. So that x bar you want it to lie between 8 and 12. For 8, so notice I'm using the new standard deviation for the denominator. The new mean is the same as the previous mean. I get these two numbers. So we are looking at the probability that x bar is between 8 and 12. Standardizing, you get z between negative 3.49 and 2.86, and you get a probability that is 0.9977. All right. So this is a rather large probability in comparison to the previous probability, 0.84. Here it is 0.99. Now, looking at these, we see that the probabilities are quite different. Why is this the case? Okay, let's come to this in our next video.